Yeah, whenever you're ready, take it away.
Okay.
Yep, I'm done.
Okay, I'm assuming you can see my screen.
Sure can.
Great. I'm no longer assuming. I have confirmation. Okay, so appreciate you all having me here. I gave some of this presentation at AGU during the PyHC session, and Julie asked me to give I don't know, a review or new version or just an update to this community. So I'm very happy to have been invited. I appreciate that. My goal for this is partially to review what I talked about at AGU for those who couldn't make it, or for those, if the audio quality was bad or whatever. But it's not just going to be a rehash of that presentation. I'm not going to focus on EPRM except to motivate. So if anybody's curious about EPRM, the simulation, I would be happy to talk to you outside of this presentation about that. And I'm going to focus more on what goats, what I want goats to be, what it is, and I guess how. And then we can talk about how it fits into this community and how people can help with it. So I've listed some collaborators here. I'm doing all the work on this now, which is just to say that none of these other people are on the hook for my decisions, and may not know as much or be able to answer questions. And I don't want to put them on the spot if you happen to know them, but they have all been invaluable for feedback and then also for earlier motivation, because Nathan especially is the originator of the EPRM model, which is the motivation for the GOATS package. And then we work closely with predictive science on other related visualization tools. Okay, so now, as I have mentioned, the EPRM energetic particle radiation environment module simulation was the original motivation for developing GOATS. So I bring that up because EPRM solves the focus transport equation, which you need not know about right now, on linked nodes, which is important to this, that move with the frame of the solar wind plasma, which is just sort of neither here nor there. It's the linked nodes part that is crucial to GOATS, because when I took over development and maintenance of EPRM, there wasn't really a good set of tools to interactively view output. There were some scripts and stuff, but there wasn't really a way to explore a simulation, which I needed in order to get my brain around how EPRM works, and which I figured would be useful for future users outside of the small group of developers or developer adjacent scientists. And so because EPRM solves this particular equation and solves these physics on linked nodes, or what we would call a Lagrangian grid, if you're familiar with that terminology, it's not a matter of simply plotting an array or visualizing a 2D array or 2D slice of a 3D array on a regular grid, because the nodes move around with the flow of, in this case, the solar wind. And so they know their own positions. They're not fixed to the quantities that we're interested in, the particle flux, the temperature, the magnetic field. These things are not fixed at certain points. And so if you just plot, nodes 10 through 100, you're not necessarily going to know where they are. And say if you're tracking the flux due to a shock or compression moving through the heliosphere, that stuff is important. So that was the primary motivation, other than just me having a hard time when I can't just open up the Python interpreter and say, simulation.run.show, here are some parameters I want to see, or something like that. And not to get your hopes up, but that is not actual GOAT syntax yet. Hopefully it will be that simple in the future. Okay, so I want to intuitively and interactively view EPROM results. I didn't want to be tied, this is another point, to a particular output file type, because that may change for EPROM. I happen to know that as the primary developer, one of the primary developers and maintainers. So I don't want anybody else to write and get fall in love with their scripts that use the, say, netcdf4 Python API, which is what you would have to use now. And then have to go in and change all that stuff for their scripts. So that's part of the motivation, right? Abstraction. That's a good practice in software development. Also related to the nodes moving around, the Lagrangian grid. I wanted to be able to interpolate between nodes, especially to a given radial distance, because often we have a satellite measurement at 0.6 AU, or increasingly closer to the sun, but we certainly don't have measurements at the specific node locations, and nodes move around with time because satellites don't care about EPROM. So that was another motivator, and that is part of GOATS right now. And then I wanted to, as this went on, it became more of less EPROM focused. I wanted to be able to seamlessly integrate observations. I wanted to have a certain observer in the EPROM simulation, and then in the same way, with same type of code, say, well, what does GOES see here, or give me an ACE observer wherever ACE was at that time, and let me compare it to these EPROM simulations. And I wanted the framework, the syntax for that to be the same. So so I would say naturally, but there were a lot of stumbling blocks, gave way to the idea of GOATS, which is an acronym for the Generalized Observing Application Tool Suite. The idea being that observers make observations of observable quantities. So that should not be anything philosophically challenging. That's a pretty straightforward motivating mantra or tagline for GOATS. And then so it's the details, or the devil's in the details, as it were, for how to implement that. But the idea here is that an observer can be a satellite, but it could also be a simulation, like EPROM. And so it has access to a data set and related parameter values. So that's important to have those things, of course. And that's pretty common, right? Like HDF files are great. HDF is great because you have the data and the associated metadata right in there. As an example, the observer knows its own metric system and its own coordinates. That's something I wanted in there because I wanted to make sure that we could work with units consistently, and it's just sort of a natural thing. If I'm flying around in a satellite making measurements, then I have a certain metric system that I'm working in, and I know my coordinates. And it hides the implementation details of its data format, which is sort of part of what I mentioned in the motivation about not being tied to, for EPROM's case, the netcdf file format, because that may change, at least for that. But also, I don't want users to need to learn another API if they don't have to. Okay, so then we get into the other two components, an observable, or an observable quantity, for which I'll use observable often as a short term, or foreshortening. Exposes metadata without loading a potentially large array. And this was important for me when I had big EPROM data sets, and I had the entire particle flux resolved into pitch angle bins and energy bins and over hundreds of time steps or whatever. This could be a very, very large array, but maybe I just wanted to know what the unit was, or as a user, you might want to know what unit does EPROM output this in, or what are the array dimensions? What could I expect to subscript in this array when I get it back? I don't want to load the whole thing, and just to get that sort of information. And so it also, an observable quantity manages user-provided observing constraints, and that'll be important for the observation part. I'll get back to that. And it colloquially, as far as I'm concerned, comes in one of three flavors. It either comes from the observer's data set. It could be a function of other observable quantities. Maybe they come from the data set. Maybe each of those intermediate quantities were themselves functions of other quantities. Those are derived observable quantities in the parlance of goats. The ones that come from the data set are primary. I call them primary observable quantities. And then you can take ratios, products and ratios of either of those, and I call those composed observable quantities. I'm just saying these because sometimes it's useful to talk about what comes from the data set and what doesn't. And I also like terminology and systems of defined words for explaining things. But GOATS does not care whether an observable quantity is a primary, derived, or composed observable quantity, and that is a feature of the package. It's agnostic to that stuff. So an observation, when you finally are ready to make one, first of all, supports dynamic unit conversion, as does the observable quantity, although that is not necessarily I guess that's that would be up to how you want to use it, which of those two you use. I'm going to skip to the third point here, because it knows the context in which it occurred, and that's related to, I'm going to switch back here for a second, related to the point here about the observable quantity managing observing constraints. So that could be, and I'll show you some code in a moment to make this more clear, more concrete. That will include the coordinates, or maybe the energy or energy range at which you want to observe something, if energy applies to it. Say it's the particle flux, or the time at which you want to observe it, or for some things like integral flux, which doesn't come out of the EPRM data set, but which we can compute. It would be what I call a derived observable quantity. You compute that given a certain minimum energy, or for one value of integral flux, you want a minimum energy above which you integrate, and so that's a parameter that you would supply, and so that's part of the observing context that the observation knows. The observable quantity passes to the observation, so it keeps track of that stuff. And then finally, to skip back to my second point here, it behaves like a NumPy array. I'm not going to get into the real implementation there, but some of you may know the ND array mixing class, and so it inherits from that. But it also supports conversion to an actual NumPy array, because why wouldn't it, if that's a natural thing for lots of people to work with? I don't want to take that away from anybody. Okay, so let me describe some of the actual details in the context of EPRM, which is currently the only implemented observer. In order to start off, I create an object representing an observer representing an EPRM stream, and that's just a stream of its linked nodes. And what it needs is, to start off, it needs its stream number, and that's an aspect of EPRM that you don't need to know about, other than the fact that every stream has a number. Otherwise, you wouldn't know which stream is which. And so in this case, the observer's ID is the stream number. But I imagine this being this will generalize to, say, the satellite's name, or for GOES the number or the letter, or for stereo is it A or B. So that would be the observer ID. And then it needs the source of where is it going to get the data, and it needs, for EPRM at least, and probably for other, possibly for other observers, the name or path to the parameter file, or the configuration file. For certain satellites, that's going to come with the data set, but in EPRM, this needs to know where that is. and you can give it a path and then any other optional observer specific things like here the configuration file after creating it. And so an alternate way to do this is just to create it with this observer ID and then go away and do something else and come back and tell it where it's going to get its data from and anything else. And the reason for doing that is to be able to switch to make the observer primary, and then to say for in the case of EPRM, switch to other simulation runs, and that may be useful in for other observers to be able to switch the sources. Say you have a downloaded file versus something that you're getting over FTP or a URL. Okay, so once I have that, I'm going to run through a couple static demos. I'm not doing these live, and this is in the directory containing some EPRM output, which is why there's no source here, because the default is just whichever directory you're in. This is what it looks like when you try to access some things that you might be interested in. So the default metric system for an observer is MKS, and so this observer can access its radial velocity, VR, and the unit is meters per second. It can access its flux, which for EPRM is sometimes a derived quantity. There's actually a runtime parameter for outputting only the flux instead of the pitch angle resolved distribution. And that's, Goats doesn't care which one it is. That's part of why. But the mean free path is definitely, for EPRM at least, a derived quantity. So that comes out in units of meters. And Goats supports certain aliases. And this is just a matter of defining aliases for any quantity. So it's something that we can change. And so MFP is a valid way to get the mean free path for this observer. And then you can also take products and ratios. Like I said, I call those composed quantities. Goats doesn't care that they are, except that it's going to parse out the symbolic algebra there to compute that, and it will compute the self-consistent unit. It will also compute self-consistent array dimensions. So it will let you know. You can ask what the dimensions of that quantity are, and it will tell you that they are the union of the dimensions of both of these two quantities. Okay, so running through the full observing sequence, it looks like this. I've created my observer. I've decided I want flux, and I've decided a priori that I want it in more common units. So per centimeter squared, per second per steradian, per MeV, technically per nuke, but these are protons in this simulation run. So I've hidden that part. And so now I have this flux, which is an observable quantity. It's not itself an observation, but I set the unit on it. So from now on, the unit, unless I change it again, is going to be this unit, and that's just for convenience. And then I can change it again in the observation. So my first step might just be to get the whole thing. I observe the flux, get back this observed, which is an observation, or I sometimes call it an observed quantity. And so I ask what its unit is. Sure enough, it is the unit I wanted, not the MKS unit. I ask what the dimensions of that array are, and it tells me the names of the dimensions, so I know physically what quantities are going into this this physical quantity. The dimensions, the dimensional quantities, and then I ask for the shape, and that's just a regular shape if you're used to using NumPy. It comes directly from that the underlying NumPy array. But I can also constrain the observation, and this was very important for me in developing Goats. I first of all wanted to be able to specify things in in plain language units, like species using the chemical symbol, radius with a number and then the unit after, or I could make this a certain number of meters, and then same for time. And these are all what I consider observing constraints. They're part of the observing context, which I referred to before. But then once I do this, I ask the dimensions again. The full dimensions of this thing are still, even though I've constrained time and radius and species, are still the time, the shell, which became a radius, and that's a radial interpolation, like I talked about before, the species and the energy, because those are still primary to this quantity flux. But the array shape is now just has all those singular dimensions squeezed out, so it's just 10. And so that would be useful for plotting, and you could plot that. You can ask for the energy from the observing context. This is why the observation knows its own context. You could ask for it, dynamically update the unit of that so that it's plotted in MEV, plot that array, which is just sequence of 10 numbers, and you get a very boring spectrum because this is just a demonstration demonstration data set. And now the next or the big project underway is to implement other observers, and this is a schematic of the of goats in the true sense, in the sense of being a generalized observing application tool suite. And this is these top rows here are really the generalized part. Each observer needs to, needs to implement its observing context. And I'm overloaded this term a little bit. I'm sorry. This is not the same thing as what I was calling an observational context before, in terms of just like the parameter values. This is the more like an application. It really is the implementation of how this observer gets its data, reads it in, maybe applies functions to it to get what I call derived observable quantities, because that will vary depending on what's in the actual data set. All the details are in this abstract observing context. And each observer provides a concrete one to this concrete observing interface. And then from that point, the user can ask for an observable quantity by name, which is what you saw earlier when I was saying stream and then bracket notation asking for flux. And the observing interface will give you back an observable quantity, and you get some metadata from that if you like to. But presumably, once you figure out which thing you want to observe and maybe adjust the units, you will pass constraints to the observe method, which I showed it in the demo in the last slide, the last set of slides. And that's where you pass your observing constraints and get an observation out of it. And then you go ahead and do some great science with that. Okay, so I'm going to walk through some of the plans, hopes, and dreams for goats, and then I'm going to move to discussion, because there were a lot of questions on the AGU chat that I didn't get to, or the post-talk chat that I didn't get to at AGU, and I also just want to leave room for that in general. So the plans are not very exciting, because those are default for for everybody, I guess. Certain bug fixes, and obviously always forever documentation, and it's lagging for goats, I know. But I actually feel like the test suite, especially for the core routines, which will apply to any observer, is pretty good. So I feel pretty good about the testing in this. So that's not in the plans, although it is, again, it always sort of comes with the territory. A little bit longer term and less well defined are certain features that I want to implement for making this more intuitive. And then I especially need to refactor and extend the data set interface, the low level interface, because right now because as I start implementing other observers, there will be lots of other data types to work with. But before that, there are certain API decisions I need to make. And so this is sort of a non-linear, these three are sort of coupled in a way that I don't quite have a clear picture of, to be honest, because this started with EPRM. It started with this one concrete observer, and then I've been working on generalizing it. And I know that I'm going to find elements of what I think are the generalized package that really are driven by the EPRM, with the tail wagging the dog, as it were, driven by the EPRM package. So these are all sort of going to feed back into each other. And then so longer term, the dream, as I'm calling it, is to implement all these other satellite observers, and that's really when goats will reach 1.0 and be a valuable tool. Begin being a valuable tool to the community. Okay, so these are, oops, I included this is the wrong version of this. This is not very descriptive, but these are some NASA grants that have been supporting this work. And here's the here are the GitHub pages and the pip install command. If you, I'm going to leave that up in case somebody wants to copy that down. So that's it. I'm going to stop there.
Thanks, Matt. Let's see. You had a couple of questions in the chat. I'll have Rebecca go first since you have your hand up right now too.
You sure? Because Will was commenting before I raised my hand.
Go ahead. Go ahead. Will, you will be answered.
Okay. Hi, this is Rebecca Ringett. I probably blasted your AGU chat with questions. But I'm one of the developers on the Komodo package. And what I want to invite you to think about is that you're doing this work for observational data, hopefully for a large range of observational data. I think at some point, maybe sooner and later, we should kind of pull together and see, okay, how are you doing this for observational data in more detail? And how would you do this for simulated data? Because Komodo is turning into a very useful interface to a growing number of model outputs. And for comparison between observational and simulated, the users are going to want to have the capability for both. So I think that would be really useful for us to get together and discuss. And there's stuff that, I mean, we've faced this along with, multiple other packages here at PyHC. We faced this somewhat similar problem for quite a number of model outputs, like how to interface uniformly between them and present them uniformly to the users. So it could go back and forth. Might be useful to you.
Yeah, that it would be nice to talk about this more in detail over email or something. Do you think that Goats is trying to reinvent what Komodo has already done or solve a problem that Komodo has already solved? Or do you think it's are you saying this is an avenue for collaboration and symbiosis?
I think a bit of both.
Okay.
Well, to be honest, your interface to the data probably would be greatly simplified by going through the happy client.
Yeah, I was hoping to talk to some people about that, or I was hoping that somebody bring that up. So thank you. I would like to.
So
I just learned about that at AGU, or I don't know. That's not true. That's a little disingenuous. But I really started exploring it after AGU. So yeah.
Yeah, we can show you how we interfaced. I mean, so almost all of the PyHC packages use Happy because it's just that great. But not everything is happyfied, according to new term. But yeah, it covers a vast majority of things. But I see pieces here that, to be frank, aren't in Komodo that our users will want for the simulated data. I mean, we also interface to observational data, but for what it's worth. But so do almost all of the other packages here with their custom interfaces directed at their domains. So yeah, don't just talk to us. Talk to the other people that do things in this domain.
For sure.
Great.
Thanks.
Yeah, I'll throw my email in the chat and leave it to you to contact me. How about that?
Sounds good.
All right.
Awesome. While you're taking a look at the chat, Matt, Will had a couple different questions in there.
I see. Yeah, I see them. Okay. Yeah, Will, are you on?
Yes. Yeah.
Okay.
Can you hear me?
Okay. Yeah, I can. So okay, let me go through these. I just wanted to know whether I can interact with you while I'm doing it.
Oh yeah.
Okay. So first question: do you also define arithmetic between observable objects rather than having to parse arithmetic from a string? Does stream? No. Short answer: no.
Okay.
Longer answer: I think I have that on a branch somewhere. I think that's it's definitely something I would like because and this is actually going to segue into your second question. I define it between unit objects and other metric objects and other metadata parameter metadata attribute like objects. But some of that stuff is some of that stuff is part of the API questions I need to answer for myself and for the package. But the idea of defining arithmetic between observable quantities would be useful. And actually, okay, let me say though that a big reason that it exists for metadata attributes like units and dimensions is because it is defined between a lower level variable quantity, which is part of the observing process under the hood for any observation. So it is not defined and on purpose for observations, for observed quantities, because the context, I can't define algebraic operations on the context, or I'm not quite sure how to do that unambiguously. But it's definitely implemented for variable quantities, which sort of which are the like I said, lower level NumPy like objects with associated metadata, and so I had to define it for the units and dimensions. But I'm not sure if I don't remember if I have defined it in much less published it in the PyPI package for the observable quantities, the pre-observation, like just metadata quantities. Okay, so I've partially answered your second question by implication. No, I don't use AstroPy units. My metric metric attribute module, which handles units, dimensions, the metric system, developed organically along with the EPROM package, which then fed into GOATs. I am sure that there's a bunch of overlap, and I have to admit that I'm not especially familiar with AstroPy in part, or really many of the other unit packages or metric system packages, because I didn't know much about them when I started this, and I like the way that my metric system module works, but I see potential down the road for collaboration or symbiosis there.
Okay. Yeah, and I guess I had one more follow-up question. I guess you sort of answered in that answer was with regards to doing like observers at different coordinate systems, and I don't know if projecting is the right word, but calculating an observable quantity in a particular coordinate system. I'm assuming that's also not done with AstroPy, given your previous answer.
That's right.
Okay, is that a system that's contained within GOATs in the way that you define particular coordinate systems?
Oh, I mean, I may have conflated a few things that confused you. An observer knows its own metric system for primarily for unit conversions, and it knows its own coordinates, but it doesn't yet do transformations among coordinate systems. For EPROM, that's a matter of EPROM thinks and outputs in spherical coordinates, and so it also computes GOATs, the EPROM subpackage of GOATs computes the Cartesian coordinates of a given observer, but I haven't thought about coordinate transforms in general.
Okay, I guess maybe that's in more of like your dreams box with regards to like ACE or PSP or stereo observations.
Right.
Okay, all right, thanks.
Yeah, good questions.
Awesome. Thanks again, Matt. We need to move on to our next presentation, but should anyone have questions, feel free to throw them in the chat. All right, so next up we have Marcus Hughes talking about regularized PSF.
Yeah, let's hope my internet doesn't flake out like it did at the beginning of this. So cross our fingers, but it seems to be working again.
Yep, you're coming through loud and clear for me.
So I should be sharing my slides now. Can you see them?
Yep.
Okay, great. So this is Coma Offit with regularized PSF. So I'll leave this here for a moment, but there's a paper that you can find that's titled Coma Offit. That's under review on the archive. And then this is also the GitHub repo. So these two QR codes should take you to them. So just a second more. If you need to get this again, I should have copied and put in the chat, but hopefully. So let's just start at the beginning about what even is a PSF. You might know, but a PSF is a point spread function. So it describes how an optical system responds to light. So it describes how the light gets spread out. So just as an example, we have some object. So in this case, it's two little circles, but it could be a star, which is just like an infinitesimally small point. And we have this PSF that says that light gets spread out. So it spreads out in this fashion. And so these two get convolved. And what we actually observe is not the circles, but this blurry image. And so this is a common, PSFs are in every instrument, but it can be problematic. So this is an example of Hubble's PSF before they corrected it. So a star, got spread out into this large extended halo. And this is an old problem, like aberrations in coma exist in telescopes since the beginning. So this is talked about in 1611 by Kepler and Dioptrice. And we still encounter it today. So the motivation of this talk is PUNCH, which is an upcoming mission that'll study the solar wind. But what we observed, so we have an engineering model of PUNCH before it's launched, and we took it out to the Texas at night and observed some stars. So here's an example of stars that we observed. So if you see a star in the middle of an image here, it looks pretty circular and point-like. But if you see a star in the top left, it has this long tail, and it's a little broader in this core, and it's got this complicated shape. If you see a star on the left here, it has a tail that's going a different way and even has a little curve in the tail. So these tails are what we're calling a variable PSF. So a PSF that was constant would mean that all of these frames look the same. But in different parts of the image, we observe that the stars look different. So we have a varied PSF across the image. And it's a real problem for PUNCH because PUNCH is not just one satellite. It's a constellation of 4 that work together. And so here you can see Wi-Fi 1, Wi-Fi 2, Wi-Fi 3, the wide field imagers, 3 of them, and then a narrow field imager in the center. But you'll notice they're doing this fun rotation. So they take lots of images and then they rotate. And they keep taking images as they rotate. So we can take all these images and mosaic them together and make a wide field composite view. And so if we think about what was happening a moment ago, let's say we have a star in the bottom right of one of these corners of one of these images. Then maybe it'll have a tail like this on image 1, this blue tail. But the same star is observed in the bottom left of another image, they overlap. Then it'll have a tail that goes this way. And so if we add these and average these images together, we won't just have one tail complicating things. We'll have multiple PSFs that make our resulting images a mess. So we want to solve that problem and make sure that these tails go away. So that brings us to the job of regularized PSF. And we're going to look at some model data to start. So what regularized PSF does is it takes images from this left process all the way to correction. So we start with a model of points. So these are just stars that are uniform brightness on a grid. And then we observe them with some fake telescope. So we have some model PSF that we have described mathematically. And so this is what you might get from your imager. And you'll notice that have all these fun little tails that are radially different. And what regularized PSF does is it takes the synthetic observation and it corrects it. So you'll see here that we have a uniform PSF now. All the stars look the same. They don't look like they would have looked without any observation PSF, but they look uniform and are nice and consistent. And so to see how well we did in correcting this image, we can apply what we call a target PSF. So regularized PSF doesn't just remove the variable PSF, it also applies a target PSF. So it removes all the variability and then it tries to make it uniform by putting a Gaussian, for example, on all of the stars. And so the way we know that this works well is the top and the bottom images here are quite similar, because this is what would happen if you had an amazing instrument that didn't have a variable PSF and you went from point stars to target. Just that's what you would observe. So this is our goal, to achieve the target. But stars don't come in regular grids and at uniform brightnesses. So we test again, and you can see it still seems to, the corrected image and the target look quite similar. And then finally, you're not always observing just stars. Punch wants to look at the solar wind, which is an extended structure. Maybe you're looking at the sun, which is obviously an extended structure to us. And so all of these nebulosities or different structures also get corrected. So you don't have to worry. It's not just a point source corrector. It corrects the entire image. So our corrected image and our target again match. So it works on Punch with our engineering data. We've gone from uncorrected to corrected. You will see that there's some residual tails that we're still working on. Our PSF model is a little crude. The data was pretty rough because it's an engineering model and it was used in the summer in Texas instead of in space. So it was much hotter than it normally operates, and the noise was higher. But overall, everything looks much more uniform, and we think on launch we'll have no problem with these residual tails. So that's what PSF, regularized PSF does. Now we're going to talk about how you can use it. We probably won't have time to get into the math behind it, but if you're interested in that, we'll also, you can reference the paper, you can email me. We can make sure that you understand the math behind it too. So pip install regularized PSF will get you the most current version, which should be 0.1.0. And it has pretty much all the functionality that you need. So once you've installed that, I would say go start with the docs. So if you go to our GitHub page, you'll see the docs are listed where docs are often listed, up here as a link. And so here's the page live right now. You can see there's a welcome and there's a quick start and some more information. We'll likely fill that in more because it's a little bit sparse, but it should get you started. While you're on the page, we would love if you start it or if you followed Punch Mission. So that's the organization that all of Punch software will be published under on GitHub. But Rebecca, you have a question?
Okay. So this work is for the Punch mission. And from what you're saying, it could be used. Well, could it be used for others, or has it been designed in such a way to be only directed at the Punch mission?
That's a great question. And it is designed so it can work for any imager. And so I'm about to show you a demo where you can see how to use it. So
okay,
hopefully
yeah.
that'll answer your question in more detail. But regularized PSF here, once again, the link, and its four main functionalities is that you can give it some images and it'll extract a variable PSF empirically from some stars in the image. You could alternatively make a PSF model by mathematically creating it. And then using whatever PSF model you have, you can correct an image. And finally, you can simulate the effect of a fake or a model PSF on some data that you have. So I'm going to switch over and attempt a live demo. Let's see how, make sure something will probably break because it always breaks in a live demo, but we'll see. So when you import regularized PSF, you'll need an array corrector, potentially a coordinate patch collection, and a simple PSF. Everything else that's imported here is pretty standard: matplotlib, astropy, numpy. So let's say you've already gone through all the work and you have an existing model. Well, you can just load it. It takes a moment because this model is kind of large, and I think the notebook's probably not still starting up. But so we have a model loaded, and now we need an image to correct. and then we'll correct it. So the thing I wanted to point out with this live demo is that that's relatively fast. You can do that in real time. It's already finished correcting. And so now we have the uncorrected image on the left and a corrected image on the right. We can zoom in and see that with this punch model, the stars are looking a little bit more symmetrical. The tails are disappearing some, and it's looking better. But what if you want to do this for your own instrument? There are many ways to build a model. You could use the stars as your test for the PSF. So we have code in the example that I'm about to show you where we extract all the stars in an image, or a set of images, and we average them to create this variable PSF model that you can use. I mentioned earlier also that you can use a functional model instead. So let's say you don't have images that have clean stars. You could define it mathematically as just an equation. And so there's an example on the website about how to do that. And then you can apply it, or maybe you need something even more unique. And so I'd be happy to work with you if that's the case. And we might even add it as a feature to regularized PSF because someone else might want it. But let's flip back over here and train a model in real time from just one image right now. So this is just a plain fits image. We could switch and use a different source if we wanted right now, but we have to define a few things. The PSF size is how many pixels wide we expect our PSF to be. So it's a little square. And the patch size is this PSF varies across the image. So how big of a region do we expect the PSF to apply to? And so in this case, it's 256 pixels. You can change these numbers and get slightly different results. But for now, we're going to use these. So I'm going to call this function on coordinate patch collection called find stars and average. And all it takes is a list of images, a list of the paths to the images, because it'll load it and try to be a little smart about not killing your memory with tons of images. And then you need the PSF size and the patch size that we just defined. So we'll run this. And it is building a model right now, and it's finished. So we just built a model from one image. We'll see in a moment that we probably need more than one image, but it's a good starting point. As I mentioned, not only does it correct the varied PSF, it applies this target PSF to make sure everything is uniform. So we have to define the target PSF. So I've defined a punch target here as just a Gaussian. So the Gaussian has a sigma of 1 in both directions. So it's a 2-dimensional Gaussian. So we'll just run this and we can see that it's a nice Gaussian. Looks normal. Looks like a little star. We convert our coordinate patch collection that we made into an array corrector. So all that's doing is it's taking that thing that we just made with the averaging and including the target evaluation and making a new Python object. Once again, we load the image we want to correct. We correct the image, and it's relatively fast. And you can see that we just corrected an image. So you'll notice first that there are all these white patches. So in this case, there aren't enough stars to actually develop a model for the entire image, because we just used one image and we don't have, like, if we zoom in over here, there's nothing there. Maybe something right there, but not much. So you'd have to include a lot more images. But on the stars that we are correcting, with even one image, we've gotten similar performance to what we just saw a moment ago. So hopefully that convinces you it's relatively easy to use regularized PSF on your own software. And that's one of the rationales of why we made it separate from the pipeline for calibrating punch and as a standalone package, so that hopefully everyone can use it. So in summary, we can quickly correct images with variable PSFs. You saw it takes only a couple seconds. And so you can do it now on your own data. And one interesting point that we talk about in the paper is that maybe we can design instruments that are a little cheaper and maybe not as perfect. And so let's think about this. Let's say that last 1% of coma and aberration improvement costs a ton of money, because like always the last little bit of precise improvement is expensive when you're designing an instrument. So instead, we have the option potentially with regularized PSF is that you could make your instrument slightly worse and correct it in software now instead. Or you can still make your instrument amazing and correct it even better, hopefully, in software. So we have a couple minutes. I'm just going to plug a few other projects that maybe I'll talk about in the future here. And then I'll ask for questions, because I don't think we have time to talk about the method. So a few other projects that are available on GitHub right now, or some of them are. Solar Annotator was something I worked on in the past when I worked at NOAA and the University of Colorado. It lets you load images of the sun and create maps of where different structures are. So where a bright region is in yellow over here, you can just draw on it and create a training set for machine learning. It uses something called Gold Solar Retriever to get the data. This may be kind of outdated now because SunPy can do this for us instead in the VSO, now that the data is available there. Another project that I'm working on now and that I was approached to actually talk about first is Tomography 2. It's an updated version of Tomography. So we take images of the sun at different times and different perspectives and recreate a 3D cube that shows what's happening in the environment using tomography. Another punch project is SOPOLPy. Ritesh Patel is working on it. It helps us convert between different polarization regimes. So let's say you have data in Stokes and you want to go to MZP, or you want to go to different polarization angles. It'll do that for you. And it'll also tell you about uncertainties and other important information. And finally, there's Punch Bowl, which is going to be the main package for Punch. And it'll be released before too long and have lots of calibration code that hopefully will be useful to the community. So with that, I'm going to open for any questions that we have.
Got one in the chat.
Yeah, we have one from Rebecca.
Oh, another one? Okay. Let me see. Where is the chat?
I could just say it. I mean,
That works
are
better.
you planning on presenting this at the SmallSat conference?
I wasn't, but maybe it's something that's relevant.
Well, I would say that the audience you're going for with this seems to be the instrumentation developers. Would that be correct?
I think it can be, but it can also be anyone who has messy data afterwards. But yeah, the instrument developers are probably thinking about it first.
Okay, that might, I would recommend looking into it. Their deadline just passed, but up to you. I'm sure there's
Okay.
others out there.
Thank you.
That's it.
Awesome. Any other
Yeah,
quick questions for Marcus?
I wanted to pop in here. I'm just curious, Marcus. Now, I know in our grad school years, you and I worked on some machine learning stuff. So I'm curious if you've had any thoughts about using machine learning to kind of figure out what the mathematics are between the blurs and the points and make it even that much easier for people to start using this out of the box.
I think that's a hard problem. And I don't know that it's necessary since we have a solution that works pretty quickly. Like, what would be the rationale of using machine learning instead of this method? Maybe you'd get better performance. I don't know.
Yeah. I would have to hear about your method, I guess. Yeah, shame we couldn't talk about it today.
Right. Yeah, it gets a little hairy. So that's why I didn't think people wanted it at 9 a.m. on a Monday.
Yeah. Okay, I see Jack's raising his hand here, so we'll jump into that. Thanks, man.
Hello, quick question. So
if I understand correctly, then the idea is to remove the spatial variation of the PSF and replace it with a known PSF. Is that correct?
Exactly. We want to
Okay.
take the spatial variation and replace it with something that's uniform, so that way you can do science more easily.
But you still have a PSF, right? For those, the target image that you're showing here and the corrected image are
Right.
still
We don't want to
affected by-
go. Sorry, I cut you off. Continue.
Yeah, they're still the point stars are still affected by PSF. You've removed the spatial variation in the PSF across the field of view. That's what this method does.
Yes, it removes the spatial variation, but it does impose an output target PSF. You could make that a really small Gaussian. So there are details about what that needs to be, but we weren't trying to go to like the original point stars.
Okay, so presumably after then, like once you've spatially smoothed your PSF, then you can just use other tools that assume a constant PSF over the field of view.
Yes.
And is that what Punch is going to do?
Right. So Punch is going to use a lot of tools, and so this was the application that I was mentioning. But there are other reasons why we need a uniform PSF. And so we will be using existing tools as well that rely on uniform PSF.
Okay, thank you. Thanks for clearing that up.
Yeah, you're welcome.
Any other questions for Marcus?
So this is Joe Plowman. I just thought I'd shout out that there's another similar method that's a bit more general but slower that I've been developing kind of concurrently, and that has a paper in the archive as well. But great talk, Marcus.
Thank you. And yes, Joe's method is awesome too, so you should check it out. And depending on your application, you might want a different technique.
Awesome. Well, thank you again to Matt and Marcus for your great presentation. Thanks to everyone who could make it today. Just a couple minutes past the top of the hour, so thank you for holding in there. And we will see you all again in 2 weeks' time. Topics TBD.
Okay,
Yeah, thanks everyone.
Thanks all.
bye.